In 1963, something terrifying was happening across America. Bald eagle nests, once filled with the sounds of eaglets and the bustle of proud parents, sat eerily empty. Our national symbol was vanishing before our eyes. By that year, only 487 nesting pairs remained in the lower 48 states, a catastrophic decline that puzzled scientists and alarmed conservationists. The mystery deepened when researchers examined the eagles. These magnificent predators, sitting at the peak of their food chain, showed no obvious signs of disease. They weren't being overhunted. Their habitat, while shrinking, couldn't explain such a dramatic population crash. The answer, it turned out, wasn't a dramatic predator or a visible threat. It was something far more insidious, a nearly invisible chemical that became more potent with each step up the food chain. This chemical was turning these apex predators into the final victims of a process scientists call biomagnification, where a seemingly harmless concentration of a toxin becomes amplified to lethal levels as it moves through the food web. But to understand how this silent killer nearly wiped out America's national bird, we need to grasp one of the most fascinating and frightening processes in nature. A process that transforms trace amounts of chemicals into deadly concentrations through the simple act of eating. This is the story of biomagnification, and it's happening right now in ecosystems around the world. DDT, or dichlorodiphenyl trichloroethane, was hailed as a wonder pesticide in the 1940s and 1950s. It was so effective at killing mosquitoes that its inventor, Paul Hermann Mueller, won the 1948 Nobel Prize in Medicine. Farmers sprayed it on crops, cities fogged entire neighborhoods with it, and soldiers used it to prevent malaria. The chemical seemed perfectly safe. After all, you could hardly detect it in the environment. When scientists tested water samples in areas where DDT was used, they found something surprising: incredibly low concentrations of the chemical, often just a few parts per trillion. To put that in perspective, imagine a single drop of water in 20 Olympic-sized swimming pools. DDT has a remarkable property that makes these tiny amounts significant. It's hydrophobic, meaning it repels water, but readily dissolves in fat. This characteristic allows it to persist in the environment for an extraordinarily long time. In fact, according to studies from the National Pesticide Information Center, DDT takes approximately 150 years to degrade by just 50% in aquatic environments. Think about that timeline for a moment. DDT sprayed during the Eisenhower administration will still be present in our ecosystems when our great-grandchildren are alive. When rain washed DDT from agricultural fields into streams and rivers, it didn't just dissolve and disappear. Instead, it began a journey that would demonstrate one of the most important principles in environmental science. Sometimes, the smallest amounts of a substance can have the most devastating effects if they're given enough time and the right conditions to accumulate. The seemingly insignificant concentrations in water were just the beginning. As this chemical moved through the food web, it would undergo a transformation that would turn these trace amounts into a devastating environmental threat. The process starts with the tiniest organisms in our waterways, setting in motion a chain of events that would eventually reach all the way to the top of the food chain, including those empty eagle nests we started with. Let's zoom in, way in, to the microscopic world of plankton, where our story of biomagnification truly begins. These tiny organisms, floating in vast numbers through our waterways, are the first step in an extraordinary process of toxic accumulation that would eventually threaten entire species. When DDT enters an aquatic ecosystem, something remarkable happens at the microscopic level. Those seemingly harmless concentrations of DDT, remember our drop in 20 Olympic pools, suddenly become much more significant. According to research published in coastal ecology journals, zooplankton concentrate DDT to levels approximately 13,000 times higher than the surrounding water. The process, called bioaccumulation, works through a fascinating quirk of chemistry. DDT molecules, being fat-soluble, easily pass through the cell membranes of these tiny organisms. Once inside, they become trapped in the organism's fatty tissues. Unlike other substances that organisms can break down or excrete, DDT stays put, accumulating over time with each exposure. Think of it like a one-way valve. DDT can get in, but it can't get out. Each time a plankton organism is exposed to contaminated water, more DDT molecules slip through its cellular membranes and become trapped in its tissues. This process continues throughout the organism's life, leading to concentrations far higher than those in the surrounding water. Initial concentration in water, 0.3 parts per million, ppm. Concentration in zooplankton, 0.039 ppm. Time required for this accumulation, just a few days. This dramatic increase in concentration happens because a single plankton organism filters many times its body volume in water each day, extracting and retaining DDT molecules each time. It's like running water through a coffee filter. Eventually, you end up with a much higher concentration of coffee grounds in the filter than you had in any single pour of water. But here's the truly crucial part. These plankton aren't just passive repositories of DDT. They're food for larger organisms. And this is where our story takes its next dramatic turn. Because what happens at the next level of the food chain makes this 13,000-fold increase look small by comparison. Remember this number though, 13,000. It's just the first multiplier in a sequence that will demonstrate why even trace amounts of persistent chemicals in our environment can become a serious problem. As we move up the food chain, we'll see how these numbers grow exponentially, creating a cascade of accumulation that would eventually reach those empty eagle nests we started with. Each tiny plankton becomes a concentrated package of DDT, ready to be consumed by the next level in the food chain. And when you have millions of these packages being consumed by larger organisms, something even more dramatic begins to happen. A process that takes bioaccumulation to the next level, quite literally. As we move from microscopic plankton to small fish, our story of biomagnification takes a dramatic turn. Remember that 13,000-fold increase we saw in plankton? That was just the beginning. When small fish feed on these contaminated plankton, something extraordinary happens. The concentration of DDT jumps by another factor of 170,000. A single small fish might consume thousands of plankton in its lifetime. Each one of those plankton is carrying its own concentrated package of DDT. It's like collecting thousands of tiny toxic sponges and squeezing them all into one container. The fish's fatty tissues. Fish tissues are particularly rich in lipids, fatty molecules that DDT loves to bind with. According to research published in environmental toxicology journals, once DDT enters these fatty tissues, it can persist for the entire lifetime of the fish. Initial water concentration 0.003 ppm. Plankton concentration 0.039 ppm, 13,000x increase. Small fish concentration 6.63 ppm, 170,000x increase from plankton. Studies have shown that DDT can persist in fish tissues for decades. The chemical's half-life in aquatic environments is approximately 150 years, according to the National Pesticide Information Center. Think about this persistence in terms of bioaccumulation. A 2-year-old fish has been eating contaminated plankton for 2 years, storing more and more DDT in its tissues with each meal. It's like adding money to a savings account where nothing is ever withdrawn. The balance only goes up. This accumulation isn't uniform throughout the fish's body. Instead, DDT concentrates primarily in fatty tissues, creating hot spots of contamination that become particularly significant when we consider what happens next in the food chain. When larger predators consume these fish, they're not just getting an average dose of DDT. They're getting these concentrated pockets of the chemical stored in fat tissues. The implications of this concentration pattern become clear when we look at what happens to predator fish that feed on these contaminated smaller fish. This is where our story begins to reveal its full complexity. The concentration of DDT isn't just adding up, it's multiplying with each step up the food chain. And as we follow this toxic trail to larger predatory fish, we'll see how these already significant numbers become truly staggering. Now we reach the devastating climax of our biomagnification story, where those seemingly insignificant amounts of DDT in water transform into a catastrophic threat to top predators. The numbers become almost impossible to comprehend. From our starting point of 0.03 ppm in water, we've watched concentrations multiply through plankton and small fish. But in large predatory fish, the concentration skyrockets by another factor of 670,000, reaching levels that would soon spell disaster for the animals that feed on them. When fish-eating birds like eagles consume these contaminated fish, the concentration multiplies yet again, this time by a factor of 8,300,000. The consequences were devastating, particularly for bald eagles. The accumulated DDT interfered with their ability to produce a crucial enzyme necessary for depositing calcium in eggshells. The result? Eggs with shells so thin they would crack under the weight of their own parents during incubation. A study published in the Journal of Wildlife Management documented that eggshells in affected populations were 20 to 25% thinner than normal. The population collapse was swift and severe. From robust populations in the 1940s, bald eagles declined to just 487 nesting pairs in the lower 48 states by 1963. The pattern repeated across other top predators. Brown pelicans, nearly extinct in California by 1970. Peregrine falcons, complete extinction in the eastern United States. Osprey, population declines of more than 90% in affected regions. What makes this story particularly tragic is the time lag between cause and effect. DDT entered the environment in the 1940s, but the devastating impact on bird populations wasn't fully understood until the 1960s. By then, countless birds had already been affected. The revelation of this biomagnification process led to one of the most significant environmental regulations in history. The DDT ban marked a turning point in our understanding of how chemicals move through food webs. It demonstrated that even chemicals that appear safe at low concentrations can become deadly when concentrated through biomagnification. Today, bald eagles have largely recovered thanks to the DDT ban and concentrated conservation efforts. Their population has rebounded to more than 316,700 individuals in the lower 48 states, according to the U.S. Fish and Wildlife Service's latest estimates. But the story of DDT and eagles isn't just history. It's a cautionary tale that continues to resonate today. As we track current-day pollutants like PCBs, mercury, and PFAS, per- and polyfluoroalkyl substances in our ecosystems, the lessons learned from the DDT crisis become increasingly relevant. The empty eagle nests of the 1960s weren't just a conservation crisis. They were nature's warning system, revealing a process that continues to threaten ecosystems worldwide. Understanding biomagnification isn't just about protecting wildlife. It's about recognizing how interconnected our ecosystems are, and how actions at one level can have profound and unexpected consequences throughout the entire food web. The DDT crisis taught us a crucial lesson about biomagnification, but new challenges have emerged that make this process more relevant than ever. Today's environmental scientists are tracking a complex web of pollutants that show alarming patterns of biomagnification, often in ways more intricate and concerning than DDT. Consider PFAS, often called forever chemicals. According to the Centers for Disease Control and Prevention, these persistent compounds have been detected in the blood of 97% of Americans. Like DDT, they're extraordinarily persistent. But unlike DDT, they're still actively entering our environment through everyday products like non-stick cookware, water-resistant clothing, and firefighting foam. Deep-sea fish now show methylmercury concentrations millions of times higher than the surrounding water. Tuna and swordfish at the top of these food chains can concentrate mercury to levels that prompt health advisories for human consumption. Cold water ecosystems show even higher biomagnification rates, with Arctic food webs demonstrating mercury concentration factors 1.5 times higher than tropical systems. Recent studies have revealed alarming statistics about microplastic biomagnification. 29% of deep-sea crustaceans and 26% of fish have ingested microplastics. Average oceanic concentration is 2.76 microplastic particles per cubic meter. The Atlantic Ocean shows the highest mean concentration at 4.98 particles per cubic meter. Arctic regions show the highest biomagnification rates for mercury and persistent organic pollutants. Cold temperatures reduce metabolic rates, leading to slower elimination of toxins. Longer food chains in these ecosystems allow for greater concentration of pollutants. High concentrations of PCBs continue to affect marine mammals. Studies of UK waters found PCBs in 91% of harbor porpoise samples. Some orcas carry PCB concentrations high enough to affect reproduction. Modern science has developed sophisticated tools to track and prevent biomagnification. Stable isotope analysis for tracking pollutant movement through food webs. Biosensors capable of detecting pollutants at parts per trillion levels. Regular monitoring of indicator species like dragonfly larvae and mussels. International treaties controlling persistent organic pollutants, regional water quality standards, and species-specific consumption advisories for contaminated fish form the backbone of regulatory frameworks. Emerging technologies include nanomaterial-based systems for pollutant detection, bioanalytical devices for rapid testing, and automated monitoring systems in critical waterways. The stakes are particularly high because many modern pollutants show biomagnification patterns we're just beginning to understand. For instance, some PFAS compounds demonstrate biomagnification factors even higher than DDT, while microplastics are showing unexpected patterns of accumulation that may affect entire food webs in ways we haven't yet fully grasped. Looking forward, several challenges demand attention. How different pollutants might interact when biomagnified together. The long-term effects of microplastic accumulation in food webs. The impact of climate change on biomagnification rates. New industrial chemicals entering the environment. Novel materials from technological advancement and pharmaceutical residues in water systems represent emerging pollutants. Global transport concerns include long-range movement of pollutants through atmospheric and oceanic currents. The lesson from DDT wasn't just about one chemical. It was about understanding how substances move through and concentrate in food webs. As we face new environmental challenges, this understanding becomes increasingly crucial for protecting both wildlife and human health. The empty eagle nests of the 1960s stand as a reminder that sometimes the most significant environmental threats aren't the ones we can see immediately, but rather the ones that build up slowly through the intricate connections of our planet's food webs. Biomagnification isn't just a historical cautionary tale about DDT. It's an ongoing process that continues to shape our environment in ways both subtle and profound. As we've traced this process from microscopic beginnings to ecosystem-wide impacts, we've seen how small changes can amplify into significant consequences. Before you move on, challenge yourself with these questions to deepen your understanding of biomagnification. A thought experiment. If a new chemical enters a lake at a concentration of 1 part per million, and we know it biomagnifies by roughly similar factors to DDT at each trophic level, what might its concentration be in top predators after moving through 4 trophic levels. Consider the multiplication factors we discussed: 13,000, then 170,000, then 670,000, and finally 8,300,000. What does this tell us about the importance of preventing even small amounts of bioaccumulative substances from entering ecosystems? We've focused primarily on aquatic ecosystems in this discussion. How might biomagnification patterns differ in terrestrial food chains? Think about factors like mobility of organisms, exposure routes, and the role of soil as a potential reservoir for pollutants. Given what you now know about how DDT and similar substances move through food webs, what chemical properties should we look for when developing new pesticides or industrial chemicals to prevent biomagnification? Consider factors like water solubility, fat solubility, and persistence in the environment. If you were tasked with designing an early warning system for detecting biomagnification of new pollutants in an ecosystem, which species would you choose to monitor and why? Remember to consider factors like lifespan, position in the food web, ease of sampling, and sensitivity to pollutants. These questions don't have simple answers, but wrestling with them helps us better understand the complexity of biomagnification and its implications for environmental protection. As we continue to introduce new chemicals into our environment, the lessons learned from studying biomagnification become increasingly crucial for preventing future ecological crises.